Let's continue with page 2 of morning test review for related rates. Number 4, back page. A street light is mounted on the 15-foot pole. A man 6 feet tall walks away from a pole with a speed of 5 feet per second along a straight path. How fast is the tip of his shadow moving when he is 40 feet from the pole? Write down the exact answer. And then we also have part B here. It says how fast is the area changing, and we'll get to that. How fast is the tip of the shadow moving? This is similar to the similar triangles problems that we've been working through that deals with these shadow problems. So we first set up a triangle within the triangle here, and we have a smaller triangle within a large triangle, and the height of the small triangle represents the height of the person, and then the height of the vertical length of the large triangle will represent the foot pole, the 15-foot pole. And then we also have a small base represented by, or the base of the small triangle represented by variable y, and then the base of the large triangle represented by x and y. So if we set up proportions here to relate x and y, we can say height of the small triangle is to the height of the large triangle, so 6 over 15, as the length of the small triangle is to the length of the large triangle. So length of the small triangle is y, and then the length of the large triangle is x plus y. So once we have this proportion set up, we can do cross product to get the fractions to go away. So we distribute the 6 through. 6x plus 6y is equal to 15y. Subtract the 6y over, we get 6x equals 9y. Now we can find, we have an equation that relates x and y. We can now find the derivative of the variables with respect to time. So 6x becomes 6 dx dt. 9y becomes 9 dy dt. We know that the person is walking away from the pole, so we know that x is going to be increasing over time, so dx dt will represent the speed of the person, 5 feet per second, at the moment when x is 40 feet. All right, so if we can find dy dt, then we can use that to find how fast the tip of the shadow is moving, because dy dt represents the rate of change of the length of the shadow, and the tip of the shadow is the sum of the two rates, the rate of the person walking plus the rate at which the dy dt, the length of the shadow, is increasing. So if we replace 5 in for dx dt, we can then solve for dy dt. So divide both sides by 9, so 30 over 9 will then be reduced to be 10 over 3, which is dy dt. So dy dt is 10 over 3 feet per second. So we have the rate of change of the length of the shadow, and then so define the tip of the shadow. Rate of change of the tip of the shadow is the sum of the two rates. So dx dt plus dy dt, 10 thirds plus 5 is the rate of change of the tip of the shadow, which is 25 over 3. Okay, part B, how fast is the area changing for the large triangle? So we want to find the rate of change of the area of the large triangle. So if we can create an equation for the large triangle, then we can go from there. So the area of the large triangle is going to be 1/2 base times height. So 1/2 height times base, or 1/2 base times height. The base is represented by x plus y. The height is 15. So if I distribute this through, I get 15 over 2 x plus y. And then if I find the derivative of each variable, a becomes dA dt, x becomes dx dt, y becomes dy dt. So to find the rate of change of the area of the large triangle, we just plug in the necessary information that we need. dx dt is 5, dy dt is 10 over 3. So 10 over 3 plus 5 is 25 over 3. Multiply that through by 15 over 2, and we get 62.5 square feet per second. Notice that with these shadow problems, the rate of change is going to be, for dx dt and dy dt, is going to be constant, so it doesn't matter how far the person is standing away from the pole. So this is information that's extraneous. A lot of times is given in the problem, but is not used. All right, number 5. At noon, ship A is 100 kilometers west of ship B. So we have ship A and ship B here. Ship A is traveling south at 35 kilometers per hour. Ship B is sailing north at 25 kilometers per hour. How fast the distance between the ships changing at 4 p.m.? Now, as A is traveling south and ship B is traveling to the north, it's not a nice shape for us to work with. So we're going to adjust the problem where we will treat one ship as static, not moving, and then we just combine the net change in distance between A and B. So if A is traveling south and B is traveling north, then that's the same thing as A standing still and B traveling the sum of the two distances. So the distance between A and B will be changing the same rate as if A was not moving and B took over both the rates together. So 35 plus 25 is going to be, well, I think in this case, sorry, I made it where B is static, is unchanging, and then A is the one that's moving. So we'll let Y represent the moving ship. X is the horizontal distance, and then Z is the change in distance between A and B. All right, so if we take the sum of the two ships and combine it to just have it be under ship A, then the two ships traveling, adding up the sum of their velocity, or of the velocities, 35 plus 25 will be 60. So we can let dy dt be 60 kilometers per hour. And we're just trying to find dz dt, right? We're trying to find how fast the distance between the two ships are changing. All right, so the equation that relates the three variables is again going to be Pythagorean theorem. So we go through Pythagorean theorem here. X squared plus y squared equals z squared. We find the derivative of each variable with respect to time. So x squared becomes 2x dx dt. Y squared becomes 2y dy dt. Z squared becomes 2z dz dt. We know that x is not changing over time, so we know dx dt is going to be 0, so that's going to take out the first term here. We can let y be equal to 240, because we know that 4 p.m. is 4 hours after 12 p.m., so 4 hours later, the ship is going to travel 240 kilometers, because 60 kilometers per hour after 4 hours, 60 times 4 will be 240. So we know y is 240. We can plug that in. We know dy dt is 60. We know z is 260 by going through Pythagorean theorem. A squared plus b squared equals c squared. 100 squared plus 240 squared is equal to z squared. So solve for z is 260, and therefore the only missing information is dz dt, and then we can solve for dz dt by just subtracting the result of the product of 2 times 260 over to the left side, and we get dz dt is equal to 55.385 kilometers per hour. Okay, part B is what is the rate of change of the triangle. So just do another practice with the triangle here. The triangle here, 100 is staying constant, but the y is going to be changing over time. So if we create an equation for this triangle, it'll be 1/2 base times height, 1/2 100, because this is a constant value, 100 times y. Okay, so here's our equation. If we find the derivative with respect to time, a becomes dA dt. This is 50, and then y becomes dy dt. So replace dy dt with what we have here, which is 60 kilometers per hour. So dA dt is 50 times 60, which is 300 square kilometers per hour. All right, number 6. This is evaluating a limit. The first thing we do with a limit algebraically is we plug in the x value to see what result we get. If we plug in 1, we get 1 minus 1, which is 0. 1 into the denominator will be 4 minus 1, which is 3. 3 minus 3 is 0. So 0 over 0 tells us that it's indeterminate form. So indeterminate form, we can either factor, but if we try to factor, the denominator is not going to quite work. So another way that we can go through, work around for these types of problems, if we get indeterminate form, is we can go through L'Hopital's rule. So L'Hopital's rule tells us that if we get indeterminate form like 0 over 0 or infinity over infinity, we can evaluate the derivative of the numerator separately from the denominator. And after we find the derivative once, we can reevaluate and plug in the x value. So x cubed minus 1's derivative is 3x squared. 4x cubed minus x minus 3's derivative is 12x squared minus 1. We reevaluate by plugging in 1. We get 3 times 1 squared is 3. 12 times 1 squared is 12 minus 1 is 11. So 3 over 11 is a real number. That's our limit. All right, last one here. This is linear approximation. So with linear approximation, our goal is to find order pair and a slope. Because if we can find the order pair and a slope, we can create our tangent line equation. Once we create our tangent line equation, we just plug in the decimal into that tangent line equation. So first step, let's find the order pair. So the order pair, we're going to choose the closest whole number to the numeric value that we see. So the closest whole number to the numeric value of from 8.04 is going to be 8. So if we plug 8 into this expression, the expression here, if I just replace 8.04 with x, this is going to be the equation we're going to work with. So if I replace 8 in for x, the cube root of 8 is going to be 2. 1 over 2 will be 1/2. So that's the ordered pair. Now to find the slope, we're going to evaluate the derivative and plug in this whole number of 8. Right? We're just trying to find the tangent line equation at a nearby whole number, x value. So we need to find the derivative before we can evaluate the slope of the tangent line. So to find the derivative, we first need to get this ready for power rule. So we bring the cube root of x up to the top, convert the radical to a rational exponent, and then we go through power rule. X to the negative 1/3, power rule becomes negative 1/3 x, and then we subtract 1 from the exponent, so negative 1/3 minus 3 over 3, or negative 1/3 minus 1, which is, if we go through finding common denominators, is negative 1 over 3 minus 3 over 3. So that becomes negative 4/3. Once we have our derivative, we can evaluate the derivative at the nearby x value. So plug 8 into x, and when we do that, we get 8 to the 4/3. 8 to the 4/3, we can evaluate this without a calculator because we can always take the cube root first. So the cube root of 8 is 2. 2 to the 4th is 16. 16 times 3 is 48. So negative 1 over 48 is our slope. We have our slope. We have our ordered pair. We can now do point slope. So y minus y sub 1 is equal to m times x minus x sub 1. Now, once we have our tangent line equation, we can isolate the y. So let's move the 1/2 over to the right side. All right, so now we're going to use the tangent line equation to approximate what the y value is at this x value, at this decimal x value. So if we plug 8.04 into the x of our tangent line equation, 8.04 plugs in for x. 8.04 minus 8 is going to be 0.04 times negative 1 over 48 plus 1/2 will give us 0.4992.